Bismillahirrahmanirrahim. My name is Jahangir Badar Sumro. I am assistant professor at Electrical Engineering Department, Sakkar IBA University. As in my previous videos, I have explained that Sakkar IBA University Electrical Engineering Department owns state-of-art hardware-in-the-loop laboratory for research purpose in the domain of power converters, smart gates, micro gates, electric vehicles, modular multi-level converters, HVDC, multi-terminal DC transmission systems, and motor drives. But in this paper, we will discuss how can we use hardware in the loop laboratory for power electronics teaching. So the focus will be power electronics teaching. Basically, power electronics is a core subject in electrical and electronics engineering at the undergraduate level. And if you move towards masters, then a good knowledge of power electronics is required to understand subjects like advanced power converters in master, modular multi-level converters for HVDC applications, or microgrids. The rapid growth in the field of power electronics requires necessary changes in the curricula and practica for power electronics. The proposed next generation power electronics teaching laboratory changes the learning paradigm for this subject and is the first time used for teaching in purpose in Pakistan. Yes, this is first time we have used controller hardware and loop laboratory or hardware and loop laboratory for teaching purpose, especially power electronics. And this is the first and only lab in Sindh and second in Pakistan after NUS Islamabad. The proposed chill laboratory enable students to design, control and test power converters without the fear of component failure. Now in this laboratory, basically students design, test their power converters, their digital controllers without the fear of component failures. Reason being, the converter is basically simulated, that operates in real-time simulation environment, that is not physical. Students do not take discrete components such as power semiconductor devices, MOSFETs, IGBTs in hands, or inductors, capacitors and analog components in hands. The circuit is in the real-time simulation mode, so there is no fear of component failure in this laboratory. Chill setup allowed the students to directly validate the physical controller without the need for any real power converter. So real power converter is not required in this laboratory. The converter is simulated, but the controller is real or physical or actual. So this setup is called controller hardware and loop, when the controller is physical, real or actual, and the converter is simulated. So this setup together is called controller hardware and loop. Now basically this allowed students to obtain more repeatable results and perform extreme digital control testing of power converters that are otherwise not possible on real hardware. So if suppose if you have a real hardware and if the controller is not properly tuned or programmed, if the controller has issues, and then it will damage the real hardware. But this is not the case in chill laboratory because it is not connected to a real power converter, but it is connected to a simulated converter. So after getting proper results in this controller hardware and loop laboratory, students can connect the same real-time digital controller to their real hardware. So in this way, the results of real hardware will be same as the results of chill laboratory. So before moving towards the real hardware, at the first stage they can verify the controllers in this lab. Alright. Furthermore, students could start learning power electronics concepts with hardware from beginning on a safe, versatile, fully interactive and reconfigurable platform. The proposed laboratory meets the Accreditation Board for Engineering and Technology (ABET) student outcome criterion K, such that students can continue with the same hardware and software toolset for graduate and research purposes. The good thing is that this is advanced laboratory which can be used for master's research as well as PhD research work, and it can be used, the same platform can be continued after undergraduate. So it meets the criterion K of the ABET. The knowledge and skills acquired during undergraduate years can help students create new solutions for power electronic systems and develop their expertise in the field of power electronics. So, this is a century which demands skills in students. So, hardware in loop is itself a very good skill, and this is a state-of-art platform for the research in power electronics. So, at the undergraduate level, they will learn new skills that will help them to get their jobs, to get a good scholarship for masters and as well as for PhD purpose. The results obtained from survey indicated that the majority of students were satisfied with the laboratory setup. They also expressed appreciation over provision of high-level graphical language LabVIEW for detailed controllers compared to conventional low-level text-based language such as VHDL, Verilog, C or C++. So this is another advantage and major advantage of this lab, that in this laboratory we use LabVIEW graphical level software. Basically, it uses graphical language. Unlike VHDL, Verilog, C or C++, which is text-based language, it takes a lot of time to learn VHDL, Verilog, C or C++. And coding using these languages is very difficult for students. But compared to that, LabVIEW is a high-level graphical language, so making the digital controllers for the power converters is easy in case of LabVIEW as compared to low-level text-based languages. The proposed versatile platform is sufficient enough to expand degrees entirely focused on power electronics. There are some universities which provide a complete degree in the field of power electronics. So for those universities which are entirely focused on power electronics, this laboratory is even good enough to be used for those universities. Now, basically, power electronics teaching is plagued by some key issues and challenges. The first and foremost problem commonly encountered is that power electronics courses often start with equations, derivations, mathematical analysis, memorization, and highly theoretical lectures that fail to engage students. This traditional approach discourages students from power electronics and is not beneficial. A literature review suggested that practical knowledge conveyed during classes should not only increase motivation but also enhance the theoretical knowledge of engineering subjects. It is essential to encourage students to have practical and hands-on experience with laboratory equipment to prepare them for real-life applications. So this is the first and foremost problem, that instead of theoretical lectures, students should be given practical knowledge. They should be given hands-on experience, and this matters a lot for power electronics learning. Now, the second most commonly encountered problem is that laboratory experience for undergraduate students is limited in most of the electrical engineering universities, as it requires high cost and physically large hardware setup. Only 46.15% of universities in the United States offer lab-oriented courses in power electronics. So if this is the situation of United States, then if we compare that to Pakistan, then certainly this ratio, this percentage will be even lower. Although most of the universities have established power electronics laboratories, these traditional laboratories are not sufficiently equipped to prepare students for careers in power electronics and cope with 21st century teaching requirements. Moreover, owing to financial restrictions, a large number of universities rely entirely on simulation-based laboratories for teaching power electronics. The findings revealed that simulation-based laboratories alone are not effective in promoting learning in power electronics courses. Digital control circuits implemented in computer-based simulations for application of power converters are far from being considered ready for practical implementation in hardware. Because if you try to deploy the same controller in real world, it will be very different from what you are simulating. Because computer simulations and hardware results, there is a lot of difference always present. So hands-on laboratory practice can prepare students for industry applications and future research. Therefore, the second crucial challenge is to provide state-of-the-art power electronics laboratories to undergraduate students where they can design, control, and test power converters. So this is the second challenge. Now the third most commonly faced problem in the field of power electronics is the preservation of continuity between hardware and software among the undergraduate, graduate and research levels. Unfortunately, most of the time, the hardware and software toolset crafted during undergraduate studies in power electronics are not versatile and flexible enough to be continued for graduate and research purpose. An engineer needs to meet ABET student outcome criterion K, an ability to use techniques, skills and modern engineering tools necessary for engineering practice. Therefore, the third key challenge is to equip its students with latest hardware and software toolset that ensure continuity for graduate and research purpose. So this platform also meets this challenge. They learn hardware and loop skills at the undergraduate level, and these skills help them for continuing their research in master's as well as PhD research work. Now the fourth most commonly encountered difficulty in the domain of power electronics is a significant gap in the education of power electronics controllers in undergraduate courses. A consistently significant challenge exists for power electronics students to implement digital controller and power converter application, and this is very true. Undergraduate students are even not able to design sinusoidal pulse width modulation technique for three-phase inverter. The reason being, what are the reasons? The reasons are explained here. Students practicing power electronics are required to have substantial knowledge of microprocessors, microcontrollers and detailed signal processors, and such knowledge is acquired with a steep learning curve. However, knowledge of such subjects may not be sufficient for implementing advanced detailed controls in power converter applications owing to the low processing and computational speed of these devices. So sometimes when they move towards advanced power converter where the number of switches are very high, as in the case of modular multi-level converter, which is recently used for the HVDC applications, where the number of submodules sometimes are maybe in 50s, 100s, and switches are more than 200, 300s. So the simple microcontrollers, microprocessors cannot handle this much complexity of switching. So what is recommended? So students should know about FPGA. FPGAs are recommended as control applications in power electronics when low jitter and highly deterministic behaviors are required. However, a student must be well versed in text-based language such as VHDL, Verilog to access FPGA boards for control system applications in power electronics. So all these difficulties in the roadmap discourage students from exploring the world of power electronics and conducting equality research in this domain, quality research in this domain. Now basically learning FPGA and programming them using low-level text-based language VHDL or Verilog is itself a challenge, and most of the electrical power students sometimes do not study VHDL or Verilog, so they have problem in FPGA, and FPGA expertise is an issue for sometimes power engineering students. So most of the undergraduate students with specialization in power system do not study Verilog or VHDL to access FPGA boards for detailed control application. Therefore, the fourth challenge is to facilitate students with advanced controls like FPGA for control and power electronics application without any prior knowledge of VHDL and Verilog, and this challenge is also overcome using the hardware and loop setup, which provides high level language FPGA, LabVIEW FPGA. So using LabVIEW, they can access the FPGA without knowing anything about VHDL or Verilog. So this is another advantage of Hill setup. Alright, in this comparison with previous research is done, it has been explained how this platform is used. Like first students can can design their controller in LabVIEW, they design their converter in multisim. Say suppose it is DC to DC converter, the circuit of the DC to DC converter is designed in multisim. The controller for the DC to DC converter is designed in LabVIEW. First they test it on their computer facility. Once they get satisfactory result on the computer, I mean offline simulation results, then they can move to real-time simulation results or hardware and loop setup. The same LabVIEW code with some minor changes is burned into MyRIO or CRIO and the same multi-sim circuit can be loaded into the PXI to get real-time simulation results. So the journey from computer simulation to real-time hardware testing becomes easier with this proposed Hill setup. And we have Open Electrical Hardware Server EHS purchased from OpalRT, which we use in this laboratory, which facilitated us to load the circuit directly from MATLAB, Plex, PSIM, Multisim into PXI directly without any mathematical modeling needed or FPGA expertise or VHDL programming. This is a setup that we have in our university. So in this case, a closed loop DC to DC boost converter is loaded. This circuit is done MATLAB and directly loaded into PXI as discussed. And the controller is burned into MyRIO, National Instruments equipment. So this is a block diagram. This PI controller is used, which is burned in the closed loop PI MyRIO, and the converter DC to DC is loaded into PXI. And this example is taken as a case study to discuss how students take the results, which scenarios are possible to simulate, and how it increases the interest and learning curve of the students. This is the real-time digital controller implemented in MyRIO, closed loop controller for the boost converter. These are the results. You see, closed loop DC to DC converter is tracking to its reference voltage. Load voltage follows the reference voltage. The results are taken under different values of proportional gain Kp. If you see, if the Kp is increased very high, as suppose in this case 0.2, you see oscillation, and these oscillations are not recommended in power converter, and this can damage your converter. You see, so a high value of Kp is can be dangerous. So students can practically see the disadvantage of higher value of Kp, and they can understand the importance of tuning the PI controller. And if the PI controller is properly tuned, as in this case, you can see the converter can reach the steady state very quickly if it is properly tuned. So they design the LabVIEW controller themselves. So this builds confidence in the students that they can develop the controller in real time. Moreover, they test their converter in closed loop, and if there is a variation in the input voltage, reference voltage from 130 to 150 volt, you see here the variation. So the controller is working properly, and within a few milliseconds it tracks the reference voltage. Or if the input voltage is changed from 100 to 80 volt, in this case, you see even then the controller is robust to track the new reference input. It can track the load reference voltage if even the input voltage is changed. And even if the load resistance changed from 25 ohm to 12.5 ohm, you can see the controller is robust enough to track this change, and the load voltage is properly followed. And then they can test their converter under different switching frequencies. Like in this case, switching frequencies increased. Increasing the switching frequency certainly reduces the ripple voltage, as seen in the table. That ripple voltage is certainly decreased when the switching frequency is increased. As in the case of 4500, we have only 0.32% ripple. And then they can test the DC loads. Like in this case, DC loads are tested in our hardware and loop laboratory. This is a power amplifier. So finally, students' evolution assessment will be discussed. These are the possible power electron modules that we teach at undergraduate level. We cover 4 modules mainly: DC to DC chopper objectives, AC to DC rectifiers, we cover DC to AC inverters, and then MMC, 3-phase multi-level inverters such as MMC. So these are the objectives that we cover in the laboratory. And this is the students' feedback that they were satisfied, the feedback was very positive. Practical knowledge delivered during class enhanced students' motivation and also improved theoretical concept of power electronics subject. With this platform, we can successfully control and design power converter in significantly less amount of time. Laboratory facility is versatile and flexible enough to be continued for graduate and research purposes. Laboratory facilitated students to implement detailed control for power converter application with great ease and excel in power electronics control education for undergraduate students. Similar practical experience must be created for other courses using this hardware loop platform. So this laboratory is not only restricted for power electronics teaching, but can be utilized for other subjects as well. Compared to analog power electronics laboratory, this Hill setup not only offers more accurate model of real industrial environment, but also provides entirely safe, fully interactive, versatile, and reconfigurable platform. The limitation of using this laboratory is a well-trained supervisor, and this hardware loop laboratory is costly. This setup is expensive. So these are two limitations of the setup. However, you can access this hardware loop laboratory remotely, and we provide services to other universities as well. If any university is interested to make the undergraduate teaching of power electronics easier for them and want to utilize this hardware and loop setup for power electronics teaching, we can offer our services. They can contact us, and we will give you the facility to use this hardware and loop setup for power electronics teaching. We will conduct lectures from here. We will give you the access of this hardware and loop setup, and we will help you to teach these concepts remotely. Thank you very much.